So we're gonna do a couple of problems like this just because it looks at the thought process in determining whether to use the washer method or the shell. Well, in this case, it doesn't really matter which one you use, and you'll get the same answer. But it tells you how to set up the equations for the two different methods, depending upon whether you're rotating around the x-axis or the y-axis. So it says set up the equations to calculate the volume of the area enclosed by the intersection of the three curves. So it's three straight lines. Y equals x plus 1, which is the red curve. Y equals 2x minus 12, which is the blue curve. No, it's the blue curve. And negative x over 3 plus 3, which is the green curve. And you can tell that just by the intersections. So the red curve is intersecting here at x equals 1. The yellow curve would intersect up at 12. It's also got a negative slope. This one, the green curve, intersects at 3. So what we're going to do is we're going to rotate that triangle around the x-axis and the y-axis using both the washer and the shell methods. And then you'll see, I think, on that handout, there's another one kind of like that I may have you guys do. So there's some more. Okay, to do. I see that my airliner is getting tired here, so let me plug up the battery before it craps out on me. So today they're releasing the big memo. At least Trump thinks it's big, huge, about supposed bias within the Justice Department and FBI. I think it's mostly people trying to gain favor with Trump. But it has nothing to do with the Russia investigation. Ha ha ha. Okay. How long does it take to undo that? I thought I charged it up last night, but let's see if this light comes on. These things are getting old, so one of these days they're going to not work anymore. Okay, so let me kind of lay out the plan here. So first we're going to do the washer method around the x-axis and the shell method around the y-axis. And the reason we're doing those two is because we use the same orientation of our rectangle. So I'm going to draw a rectangle in here. So it's a skinny rectangle. Actually, I'm going to draw two rectangles just to... So when we rotate around the x-axis, we're going to create washers. So around this axis, you'll see the washer. And you'll notice that the top of the rectangle changes between the two that I show. For part of the stacking of the washers, the red curve is the top curve. But for the other part, it's the blue curve that's the top. But the green curve remains the bottom of the rectangle for the entire interval, from where you have the intersection of the red and green curves there and the blue and green curves there. So the first thing we actually have to do is figure out what those points are, because if we don't have those points, then we don't have the limits of integration. So to find the points, just like we did the other day, except this is a little easier, is we're going to set each one of these equations equal to the other and find the points of intersection. So for example, I'll do the first one. If we're looking for the intersection of the green and the red curve, so the red curve is, let me just underline them so I'll know what's what here. So this is the red curve, this is the blue curve, and this is the green curve. Okay, so to find the intersection of the red and the green, you're going to say x plus 1 equals negative 1/3 x. That's the same as negative x over 3 plus 3. So if we add 1/3 x to both sides, we'll get 4/3 x over here. And if we subtract 1 from both sides, we'll get 2 over here. And then you'll multiply by the reciprocal of this. So if we multiply by the reciprocal of 4/3, we get 3/4, which gives us 1. And so we'll multiply by 3/4, which is, so it's 2 times 3 over 4, which is 3/2. 6/4, which is 3/2. So that's the x value. And that's what we need at this particular point, is the x value. So that's my first. And you can see it's 2/3. Yeah, right there. So you can see it's intersecting right here at this mark, which is 2/3. I mean, 3/2. Okay, so go ahead and figure what the intersection of the other two curves are. So you're going to do the red and the blue and the green and the blue. Just set them equal to each other. Do some simple algebra. We'll ultimately need the y value as well. So I'm going to go ahead and, so for example here, all I have to do is plug this x value back into either one of these equations, which this one looks easier, so I'll do that. So you get, you'll get 3/2 plus 1. So the y value is going to be 5/2. So you see there's 2, there's 3, that's 5/2. So the coordinates of the intersection of this will be 3/2, comma, 5/2. So that's the green and the red. Yeah, it's probably some way to do this on your calculator. But so if anybody did it, you can check my answers. I think it did. I'm going to double check here. Yeah, they look right. Okay, so here are the red and the blue curve. So those equal to each other. Solve for x, you get 11 thirds. Plug that back into this equation, you get 14 thirds. And then set the blue and green equations to each other. When you add 1/3 x to both sides, you'll get, this is negative 6 thirds, so it becomes negative 5 thirds. Subtract 12 from both sides, you get negative 9. Multiplied by the reciprocal to solve for x, you get 27 fifths. And plug it back in this equation. You could, either one would work. You get 6 fifths. So those are the points of intersection. Okay, so those are going to be our limits when we need them. Okay, so now the first thing we're going to do, we're going to add a page here. So the first thing we're going to do is the washer method rotated around x-axis. So if you remember, the washer method says that the volume is equal to pi times the integral from a to b of capital R of x quantity squared minus small r of x quantity squared times dx. So we have to figure out what the limits are. And because we have two intervals, we have to go from the intersection of the red and the green curve, the x value, to the intersection of the red and the blue curve, x value. So that's one integral. And then you're going to have a second integral where you go from the intersection of the red and the blue curve, x value, to the x value of the intersection of the green and the blue curve. So what we're going to do is we'll put it in, write it into two parts. So the answer is pi. So we take the integral from this x value, which was 3/2. So that's the lower limit. And then we integrate to the x value associated with the intersection of the red and the blue, which is 11 thirds. And in this case, the outside radius is the red curve. So whatever that is, sorry, red curve, there we go. So you're going to have x plus 1 quantity squared. So in this case, let's just write it out. R of x equals x plus 1. Then you're going to subtract small r of x, which in this case is the green curve. So you'll take minus x over 3 plus 3 quantity squared. So that's small r of x equal to negative x over 3 plus 3. And then you put a big parentheses around that and multiply by dx. So that's the first part. Then you have the second part. So now you integrate from 11 thirds to the x value. So then you integrate from this x value to this x value. So we need the x value of the intersection of the green and the blue curve, which is 27 fifths. Now the green curve is always going to be the one that's on the inside, so I can copy that down again. That's small r of x. So again, r of x equals negative x over 3 plus 3. And the first part, the outside radius, is the blue curve. So the blue curve is negative 2x plus 12. So we put negative 2x plus 12 quantity squared, the whole thing times dx. Okay? Anybody got any questions about anything I did there? Yes?
So for the integral for the second equation, how come the 27/5 is above the 11/3, like when you were going to look at them?
Well, that's the x value. You're looking at the y value.
Oh, that's it.
So when we integrate with respect to y, yes. Okay? Yeah. So, yeah, if we go over here, the x value of this intersection is, you can see the sequence. This one's first, that one's second, that one's third. When we do the y direction, this will be first, this will be second, that'll be third. Okay. Okay, we're not going to integrate that. Okay, it's your last chance. No, it's not last chance, but until we move on to the next. So now what we're going to do is we're going to repeat that procedure. Luckily, we've got a lot of stuff already figured out here. We're going to do the shell method around the y-axis. Okay, so let's do that. So we're going to rotate around y-axis using shell method. And the reason we're doing that next is because the rectangles look the same. It's just now, instead of rotating around the x-axis like that, you're going to rotate around the y-axis. And instead of creating washers, which are thin things with a bigger dimension this way, you're going to have the shells, which are going to rotate this way, and the small dimension is the thickness of the shell, whereas for the washer, the small dimension is the width of the washer. So we're going to go about that, but you can see the rectangles look the same. So that means we're going to integrate with respect to x. It also means that the limits of integration are also going to be the same. So we're going to have the same limits on the integrals, but the integrals are going to be different. So if you look in the book or look in your cheat sheet when you do the test at some point, you'll find out that the volume using the shell method around the y-axis is 2 pi times the integral from a to b of p of x times h of x times dx. So notice a and b, notice x, but we've got these two other functions that we've got to figure out. Well, if you look at your notes from the other day, when rotating around y-axis, p of x equals x. So that's easy. We got one of them. It's kind of a default. So all we have to do is figure out what h of x is. Well, h of x is the height of this can at that particular point. So this is one side of the can, this is the other side of the can, not the thickness, but the extent of the can. So to find this height, all I have to do is take this function and subtract that function. When we use the washer method, we had to take this squared minus that squared. But in the case of the shell method, we just take the difference in the two, not the difference in the squares. So let me, so what I'm going to do is here use some color here. So for the red-green part, meaning for this part, h of x equals the equation for the red line, which was, what was it? It was x plus 1 or something like that. Yeah, x plus 1. Okay. So it's x plus 1 minus the green curve, which was negative 1/3 x plus 3. We could simplify that, but I'm just going to leave it as it is, just to show you. So that's the height of this. Before, if you look back at the washer method, it was this squared minus that squared. Let's just verify that. So it was this squared minus that squared. For the washer method, it's just this minus that. Now for the next part, which has blue on the top and green on the bottom, so that's the blue-green. So here's blue-green. Now the blue curve is on top and the green curve is on the bottom. So you're still going to have this negative 1/3 x plus 3. That's the green part. But the blue part was negative 2x plus 12. So that's h of x for the second part. The blue curve minus the green curve. Again, if we go back and look at the other case, we squared this squared minus that squared. For the shell method, we just take this minus that. Sorry, bouncing around here. Okay, so finally, here's the answer. Okay, so the volume is equal to 2 pi times the integral from whatever the limits were, 3/2 to 11/3, or, yep, 3/2 to 11/3. The second, I'm going to write these out so I don't have to keep bouncing back and forth. The second integral will be from 11/3 to 27/5. And then all I have to do is p of x is x, and h of x is that. That's for the first part, the red-green part. And for the blue-green part, x is still p of x, and h of x is negative 2x plus 12 minus a negative 1/3 x plus 3. Oh, there. So that's it. So that's the integral. Again, you multiply everything out, combine like terms, integrate the polynomial. This one's going to be easier, right? Because all you're going to do is subtract two linear equations to get you another linear equation, multiply by x. Whereas the other one, you're going to have to square stuff, and then you're going to have x. It's just more difficult to do the washer method in general. Okay. Anybody got any questions about how I got that? Okay. Now, moving onward. Now, I hate to do this to you. I should have 2 of these on the paper so you could draw them, but and I was going to try to make an extra copy this morning, but I didn't get around to it. So now what we're going to do is we're going to rotate the rectangles to be like this now. So instead of having vertical rectangles, we're going to have horizontal rectangles. So what we're going to do with that is we're going to use shell method to rotate around x-axis. So we've done the washer method around the x-axis. Now we're going to do the shell method around the x-axis, and then we'll do the washer method around the y-axis. So let's just write out the equation. Equation shell method around the y-axis is 2 pi times the integral from c to d of p of y times h of y times dy. So now the next two possibilities are integrating with respect to y instead of with respect to x. And you can see that by the rectangles. You know, what we're doing is we're stacking up those rectangles, which you're going to have a vertical stack. So that's why you're adding things. You're adding things together in the y direction. So now we're going to use the y coordinates of our intersections to find the limits. We also need to rewrite the three equations in terms of y. So that's what we're going to do first. I'll do the first one. I'll let you do the second two, or at least you give you a head start in it. So let's see. The three equations were y equals x plus 1, y equals 2x minus 2x plus 12, and the third one was y equals negative 1/3 x plus 3. So this one's easy. So to solve in terms of x is equal to y minus 1. So all I did was move that to the other side. So go ahead and solve these other two equations for x. And that gives you, when it says x equals something, that's f of y. So this one's going to have a fraction associated with the slope. This one will have a whole number ultimately. And they still stay the same color, so so this is my red curve now. And while you're doing that, I'm going to grab the limits here so I know what they are. So I don't have to keep jumping around. Okay, 5/2, 6/5, 5/2. So that's what I got. So I've subtracted 12 from both sides. divide by -2. And what I was doing was I was checking here you can check the y-intercepts, here you can check the x-intercepts. So this red curve has an x-intercept of -1. The green curve has an x-intercept of 9. The blue curve has an x-intercept of 6. So at least those numbers are right. And I wrote down the intersection. So the lowest intersection is 6/5. This intersection in terms of y is 5/2. This intersection is 14/3. So those are going to be my those are going to be my things that I'm going to do the limits on. Oops. Okay, so now we can do everything. Well, have we done h of y yet? We're going to have to do that. Okay, so let's again, what we're going to do is the first part, you're going to have this as your upper curve. In this case, the outer radius or the upper curve is always going to be blue, and the lower curve changes from green to red. So we're going to have a blue-green and a blue-red. Okay, so blue-green and a blue-red. So the blue curve, what do we say? That's always the bigger one. Okay, so that's going to come first. So we'll take this function. So h of y for this particular case is going to be -1/2 y plus 6 minus the green curve, which is 9 minus 3y. So this is the blue, and that's the green. And for the second case, h of y equals, again, the blue, still blue, so it's going to be -1/2 y plus 6 minus, so that's blue, minus the red, which is y minus 1. So that's red. So and remember, one other thing we've said is that in this case, p of y equals y. So because we're rotating around the x-axis, the y value or the radius is always just y. So we're going to write the answers in here. So the volume is going to be it's going to be the sum of these two. So I'll put the answer between these two so we can see them. So let me just move this down a little bit. So what we're going to do is we're going to integrate from 6/5 to 5/2 y. P of y is y. And then we're going to multiply by h of y, which is -1/2. Make sure I'm doing the right one here. So I'm doing the green blue. Yep. Okay, that's good. Plus 6 minus 9 minus 3y. The whole thing times dy. And then we have the second part, which is the integral from 5/2 to 14/3 of y. That's the radius times -1/2 y plus 6 minus y minus 1, the whole thing times dy. So remember, this is the blue part. That's the blue equation. That's the green equation. That's the blue equation. That's the red equation. Okay. Yeah, it takes a lot of thinking here, but it's not, we're dealing with linear equations, so at least the algebra is not that difficult. It's just, so we've got one more to do here, and that's using the washer method around the y-axis. But again, we've already got the equations in terms of the right variables. We have the limits of integration, so it's actually going to be, it'll be a piece of cake, right? So I'm just going to add a page here. And so what we're going to do, rotate around y-axis using washer method. So that's our last thing. And the equation is, washer method just has pi. You integrate from c to d of r of x, which is the outside radius, squared minus small r. It's a function of y, not x. Okay, fix that. Ry, the whole thing times dy. So again, we can use what we already know. This is the outside radius, which is the blue curve. This is the inside radius. So all we have to do in this case is we take the same limits, 6/5 to 5/2. Instead of multiplying by y, what we're going to do is we're going to square that thing. So you'll have negative 1/2 y plus 6. So that's the outside radius. And then you're going to subtract the inside radius squared. And you can multiply the whole thing times dy. So that's half, and then not numerically half, but it's half the work. And then you integrate from 5/2 again to 14/3. And I'm going to take these two, which define the height in the shell method, but define the radius in the washer method. So actually, some people ask me if I ever do extra credit, and I have never done extra credit before, but I just had a thought. So if you want some extra credit for the last test, do those integrals and show that they're equal to each other. That the value you get by using the washer method and the shell method around the x-axis give you the same number, and if you take the washer method and the shell method around the y-axis, that you get the same number. Okay.
Do we just have to do that before the last test, or is this for the next test, or this for the final exam?
This is for extra credit for the test you just took, which you don't know what you got on it yet. So I'm not putting a date on it. I mean, it'd be nice if somebody did it before we take the next test, because I'd like to say, hey, it works. Might even copy your solution and hand it out or something like that. But, we're not spending time in class to do it, but it would be, it's a satisfying thing to do, believe it or not, at least for some people, to do that. Because the equations look so different. One you're using the y limits, the other one using the x limits, all this stuff, but ultimately you'll get the same answer, which is that's pretty cool. So on Monday, I'm not quitting yet. Don't worry. Don't get excited here. I think I'm going to save this for just a second. Save as. I'm going to assign the homework for. Yesterday I had some. I don't know if I would call it free time. I just decided I wanted to do something different. So I was recording lectures for pre-calculus in anticipation of next year. Okay, so let's say this is, we'll just say in class 2018. Okay. So let me open up. I think I've assigned section 2, right? Homework. I hope I did. If I didn't, let me know and I'll give it to you. But there it is.